Hello, today I'm going to go over the pink sheets for Unit 5, and we're starting off with 4 ways that you can prove two triangles are congruent to each other. So the best advice that you can use, that I can give you, is to always draw a picture. Always draw a picture, or really, usually one will be provided, but always mark your picture. And when I say mark, using either hatch marks for the sides or arcs for the angles. So there's 4 ways that you can prove triangles to be congruent: side, 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 angle, angle, and angle, side. Notice that there's two other common misconceptions about other things that might be possible. There's no angle, side, or side, angle. It's the same thing, just different order. And there's also no angle. There is side, but there's no angle. So none of these are possible. The first 2, like I said, are exactly the same thing. So if it spells a bad word, or a somewhat bad word, that's not one of them that we're really using. So just be aware of that. And okay, so on to the ones that we are using though. Side is the first one that I'll explain. And that says if all 3 sides of a triangle are congruent to all 3 sides of another triangle, then the 2 triangles must be congruent. So let me try to draw 2 triangles. May not be exactly the same, but I'm going to label them A, B, C, and D, E, F. And I'm going to say this side AB has a single slash, so does DE. BC has a double slash, so does EF. And AC has a triple slash, so does DF. So, since you have one side, in the first one being congruent to this one side in the second, a second side congruent to a second side, a third side congruent to a third side, you have side. You can go around all 3 sides, and you go in the same order: 1 slash, 2 slash, 3 slash, 1 slash, 2 slash, 3 slash. So we can write a congruence statement. Say triangle ABC is congruent to, and make sure you're going in the same order. This is single slash, double slash, triple slash. Single slash, double slash, triple slash. So we have to go in the same order, which means DEF. Oops, triangle DEF. So triangle ABC is congruent to triangle DEF. So that was the first way you can prove triangles congruent. This is actually probably the easiest one, because if you have all 3 sides congruent, then that's pretty easy to show. Where it gets harder is where you start involving the angles, and you just have to be a little more careful. So side, angle, side. Let me try to draw one like that. That would be, say, triangle RST and XYZ. And side means we have one side in each congruent, an angle, and then at a second side. So what we have to have here is we need to talk about what kind of angle that is. You have 2 sides and the included angle. Included means it's in between those 2 sides. So if 2 sides and the included angle of one triangle are congruent to 2 sides and the included angle of another triangle, then those 2 triangles are congruent. So this right side is going to be pretty similar the whole time. We can say triangle RST is congruent to triangle x, y, z. And you can put these in, you can start off the first triangle in whatever order you want with the letters, but remember when you're writing triangle congruence statements, the order does matter, especially for the second triangle you're writing. It has to match exactly the same order that you're going in for the first triangle. Angle side angle congruence would be really similar to side angle side, except as you might imagine, instead of two sides being congruent, you only have a single side and then you have an angle. So I'll say this is triangle KLM, and yeah, I'll say PQR. And what do we have here? We have angle side angle. So we have angle side angle, angle side angle. So we have one angle being congruent. The included side between the two angles is also congruent, and a second angle is congruent. So again, we're using the word included. Last time it was included angles in between the two sides. Now we have an included side between the two angles. In either case, you're going to have something included, but this time we have angle side angle, angle side angle. So we can write our congruence statement. We can say triangle LMK is congruent to, and that would be triangle PQR. LMK PQR. This is kind of a simple case because in all of the drawings I'm making, we're lining them up exactly the same. Keep in mind, sometimes one of them can be flipped over, can be rotated, it can be upside down, it can be all sorts of things. So just keep that in mind. It's not always as simple as these drawings make it seem. Okay, so we've done 3 out of the 4 ways. There's one more way, and I'm going to try to draw this one a little bit different just to give you some variety. I'm going to try to make these look congruent. So triangle HIJ and TUV. That's a U and a V. Okay, so this is angle side congruence. So that means going in one direction, I need an angle, a second angle, and a side. So going with the other triangle, I have all in one direction, angle, angle, side. So you have to go in this in a continuous direction, angle, angle, and then I come across the side right after that second angle. Angle, angle, side. Realize though that I can't go the other way, not in this drawing anyway. Angle, I don't have an angle here, so that doesn't really count. I can't go that way. Angle, angle, and then immediately after that second angle, I have this side. So we call that side a non-included side. So I have two angles and a non-included side of a first triangle are congruent to the same of a second triangle. Then if that's the case, you have congruent triangles again. So triangle HIJ is going to be congruent to triangle HIJ, so that's TUV. So we just showed you 4 different ways that you can prove triangles congruent. Let's go on to the second page. And some additional notes to know about some words we just talked about. What is the included angle? That was an angle formed by the adjacent sides of a polygon. Doesn't necessarily have to be a triangle, it can be any polygon. So an angle in between two adjacent sides. An included side is a side between two angles of a polygon. And really, I would say two consecutive angles of a polygon. I would probably modify this. A side between two consecutive sides of a polygon. Okay, well, we already talked about this in the previous lesson, 5-1, but CPCTC, what does that mean? Well, if you spell out the words, corresponding parts of congruent triangles are congruent. So what it says, if you have two triangles that are congruent, then all of their corresponding parts are congruent to each other. Okay, there's not much you can really write down about that, but when you do talk about that, pay very close attention to the congruence statement that they're giving you or that you're writing down. Whenever you're writing down your congruence statement or you're seeing it written down, the order matters a lot. So be really careful with the order. Okay, what's the definition of perpendicular lines? If two lines are perpendicular, I'm going to just draw some line segments. You can use lines or line segments. Then all it's really saying is they form right angles. So let's say XYZ, and then say I'm just going to call these segments. Segment XY is really just going to be perpendicular to the other one, segment YZ. Well, if I have two segments or two lines being perpendicular, what do I get? I get a right angle out of that. So what is this angle? Angle XYZ is a right angle. That's all there is to it. Okay, so perpendicular lines must have a right angle. You probably already knew that anyway. Right angle, well, but now we have a reason why we can use this in proofs, or why we can write these statements. Right angle congruence statements. If two angles are right, if they're both right angles, and I'm going to call that angle 1 and angle 2. So if they're both right angles, then they are congruent. So if angle 1 and angle 2 are right angles, then if they're both right angles, then they're both congruent to each other. So angle 1 must be congruent to angle 2. Again, that's pretty straightforward, but this is a reason you will use in some proofs. Definition of segment bisector. We've talked about angle bisectors, but I don't think we have ever talked about segment bisectors on the pink sheets. So this is where we're going to do that. If a line, segment, or array is a segment bisector, then it intersects the segment at its midpoint. Bisector, remember, means you're cutting something into half, two equal halves. So say that's A and B, and then we'll just say it's being intersected right there by line L. So line L bisects segment AB. If it's bisecting segment AB, that intersection point is the midpoint of AB. So then what is our conclusion? then M is the midpoint of segment AB, which you can go further. If you want to use the definition of midpoint, then you could say, well, I know the measure of AM is equal to the measure of MB. Anyway, so that is your first 2 pages of your pink sheets.